In the last video, we talked about the data sheets of different ICs, and in the video previous to that, we talked about simulation of basic gates in the Proteus environment. So, in this video, we are actually going to look into these ICs, what are different families available, how do we connect them in a circuit. An IC is the basic component that can perform various functionalities for us. Well, these functionalities could be as simple as a basic OR gate, AND gate, or it could be as complex as our modern processors. So let's have a look into these ICs and their different aspects. An integrated circuit is a collection of various electronic components on a semiconductor substrate. Transistors are the main components that are part of an integrated circuit. However, many other electronic components like diodes and resistors are also part of an IC. So this collection of all the components also referred to as a chip, which is the final physical form of an integrated circuit. It is usually enclosed in a protective plastic coating, and we have the connection points or leads or pins of an integrated circuit coming out of that plastic coating. This coating could be plastic or ceramic or any other suitable material. So these pins which we physically see coming out of this package, they are basically used to connect this device to other devices or connect this device in a printed circuit board, or in our case these pins allow us to mount these chips on a test board, on a Vero board, or on a breadboard, and then we can supply it power, and then we can apply the inputs and out and then we can apply the inputs and observe outputs. Now digital systems rely on these ICs, and they have been in use, and that is what really has accelerated the growth of all the digital world we see around us. ICs can be classified based on a number of parameters like complexity, the technology of the transistor being used, and the way these ICs are actually made part of a bigger circuit. We are now going to look at these classifications in more details. So the complexity of an IC basically refers to the number of logic gates that an IC contains. And this parameter is known as scale integration. So we have ICs like SSI, MSI, LSI, VLSI. So we have small scale integrated circuits, we have medium scale integrated circuits, then large scale integrated circuits. This table shows the gates per chip for each of these integration levels. So the ICs that we are going to use in this lab, they mostly fall in the category of small scale and medium scale integration, and the modern processors and chips that implement quite complex functionalities. They literally contains millions of equivalent logic gates on their chip. One extreme, we have ICs that implement very basic logic functionalities like AND gate, OR gate, maybe adders, subtractors, while on the other extreme, we have some really powerful ICs that are implementing the processors and system on chips. The next classification that we are going to talk about is the classification of the ICs based on the technology. So by technology, we refer to the transistor technology. As we discussed earlier, the main component of an IC is the transistor that is being used to build up the overall functionality of the IC. Now the transistors could be classified into two main families, bipolar and unipolar. Bipolar ICs have BJTs or bipolar junction transistors as their main circuit element. The classic TTL family, transistor logic, belongs to this bipolar IC configuration, and we would be using this TTL family logic ICs to conduct our labs in this course. TTL family is one of the most widely used bipolar ICs, and it has been in use for several decades now. Although the modern CMOS logic family has replaced, or you can say overtaken, TTL in terms of the processing power and power consumptions, but the TTL family is kind of a legacy thing that is being used in various electronic devices. This diagram is basically showing the construction of a two input NAND gate using TTL logic. We would not be going into the detail of this circuit, but I hope you can identify that there are six transistors being used in this circuit along with other components like resistors and some diodes to implement the functionality of a two input NAND gate. Within the TTL family, we have different subfamilies. These subfamilies can be identified with the prefix. For example, 7404 shows the standard TTL inverter commercially available, and 74S04 denotes the Schottky TTL inverter. The hex inverters written in the bracket basically shows that this chip or IC74S04 or 7404 basically contains six such inverters or NOT gates. So 74 denotes the standard TTL, and if 74 is followed by some alphabets, so these alphabets denote the subfamily of the TTL family. The last two digits or the number at the end basically shows the functionality of the IC. So 04 shows that this IC is an inverter. The transistor technology that is the most widely used one now and has really resulted in the modern computational revolution is the one based on unipolar transistors. The complementary metal oxide semiconductor logic family is one of the most widely used, and our modern processors and chips are built on this technology. Basically refers to the presence of both NMOS and PMOS transistors to build a logic gate. A typical two-input NOR gate made using this CMOS technology or made using NMOS and PMOS transistors would look something like this. Without going into much details, we can see that four transistors can be used to achieve this logic functionality. The modern ICs that we used are built upon this CMOS technology. From a practical point of view, one of the differences between TTL and CMOS logic is the voltage levels for high and low logics and the operating voltages. This table lists the various versions of two-input NOR gates that are available in CMOS family. The legacy or the classic CMOS ICs that implement basic logic gates start with the prefix 40. Also, there are ICs that could be compatible with both TTL and CMOS logic families. For example, if a C is added to the 74 series, it now shows that it's a CMOS logic IC and it is pin compatible with TTL. Pin compatible means that if you could take out a 74 TTL family IC from a circuit and plug its CMOS equivalent 74C, the pin numbering or connections would need not be changed. However, the voltage level and the operating voltages would be different for the replaced CMOS IC. Similarly, a T followed by C in prefix shows that CMOS family IC is actually both pin and electrical compatible with the TTL family. The quad here means that there are four instances of NOR gates on this IC, and 02 is the identifier for the two input NOR gate in the 74 series, and 01 is the identifier in the 40 series. By mounting configuration, we actually mean how the ICs are physically made part of the circuits. They could be surface mounted or through hole mounted. The name indicates the through hole ICs are literally inserted through the holes available in a printed circuit board. Dual inline package or DIP ICs are the most commonly available through hole ICs. The major advantage of these ICs is the ease of placing them in a circuit and taking them out. The mounting configuration is the surface mounted technology. It is a space saving alternate to the through hole mounting. As you can see, the pins of these ICs are more suitable for fixing them once for all. So it is not easy to take them out and replace them once they are made part of a printed circuit board. Next thing we are going to have a look at is the pin numbering of these ICs. The DIP and the SOIC package have the numbering arrangement as shown below. Usually the IC contains a physical depression or a notch or a pin identifier. As you can see, the pin 1 starts to the left of this notch and continues in a counterclockwise direction. Now let's see some of the examples of the TTL ICs. These are the ICs that we would be using in our course as well. So for example, if we look at the two input AND gate in TTL family, the number for this IC would be 7408 and it would be containing 4 AND gates as shown in this diagram. The pin 14 or the VCC pin would be used to supply the voltage and 7 pin is for providing the ground. For an OR gate, the IC number is 7432 and the pin configuration is very much like the AND gate IC. 7404 is the TTL inverter IC. Now this IC contains 6 inverters and we can see that the pin 7 is reserved for ground and pin 14 for VCC or the operating voltage, very much similar to the ICs of and NOR gate in the TTL family. Now we know about different IC families and we have talked in detail about the TTL families. So let's see how can we actually take a TTL IC and patch it on a breadboard. A breadboard is a basic patching board where you can place your ICs and connect them to inputs and outputs and other ICs. So if we want to place an TTL IC on a breadboard, we have to place it like this. So if we place an IC like this, it would be a wrong placement since the pins on both sides would be connected to each other. On a breadboard, the vertical darts are all connected together and similarly the horizontal darts you can see above these red lines, they are connected together. A very important tool that we use for debugging of our circuits is a logic probe. A logic probe can be used to monitor different signal levels within your circuit. So usually it has a visual indicator or LED. If the LED is on, it indicates a logic level high, or if the LED is off, then it means that the logic level is low. Another version of the logic probe has different visual indications for logic low and high. For example, the red usually refers to the logic 1 and logic 0 is shown by the green LED. Now we are going to talk a little bit about some properties or parameter of ICs. One of the most important parameters is the loading factor or fan out. It can be roughly defined as the number of logic inputs that the output of a logic gate can drive reliably. For example, if an inverter has a fan out of 4, then its output can serve as input to further 4 inverters. Fan in is simply the inputs of a logic gate. So a 2 input AND gate has a fan in of 2 and a 3 input AND gate has a fan in of 3 and so on. Another important parameter of the IC is the power required or dissipated by a gate to achieve its logic functionality. It is usually given as the output current ratings, which can then be used to calculate the power. Propagation delay is the time taken by a signal from input to reach output. As you can see in the waveform below, signals in real world always experience a delay. For example, in case of an inverter, the output seems to appear almost at the same instant the input is applied. However, there is a fine delay involved that might not be noticeable for us, but it is very much there. So the real output waveform shown as red in this diagram is somehow shifted by a few micro or nanoseconds. There are different parameters of an IC, but where do we get this information from? Manufacturers provide a technical document for this purpose, which is known as a datasheet. A datasheet contains lots of information about an IC, like its functioning, its pin layout, connection diagrams, and physical appearance. Understanding the datasheet is an essential step in using digital ICs.